All right. Can everyone hear me? Oh, that's so much better. Cool. Welcome to United Astronomy Clubs of New Jersey. We are here on site in Jenny Jump State Forest in Hope, New Jersey. And I want to welcome everyone who is here, not only joining us here in person, but also joining us online because that's right, we do live stream these to both Twitch and YouTube. So if you ever can't make it out and are looking for something to do on a Saturday night at 8 p.m., do feel free to join us there. Stop in, say hello and chat, or and enjoy the presentation and ask questions as we go. So since I think I just saw someone pull in and park, I want to give them a couple minutes to rush down here and get settled in. I do want to encourage everyone to check us out on our website, uacnj.org. It's where you're going to find a list of all of our upcoming talks, as well as information about our member clubs, because we are actually a club made up of other clubs. And some of the easiest ways to get involved in astronomy is to go see your local club, not only because they're close to you, but because they're going to have all those tips and tricks for viewing in your local area. Because, no offense, I'm used to viewing out here, and the tips and tricks I know probably aren't quite as effective when you're coming from New York City. Uh, they're going to have little hints like where's the best place to view this or what's the cool astrophotography shot. Do go check those out our member clubs to see who's closest to you. In addition, do follow us on our social media channels, our Facebook, our Instagram. We have a Discord server. Not only are they great places to see what we're up to, but also places to get your questions answered or show off your brand new rig you just bought at NEAF, the Northeast Astronomy Forum. Because, which speaking of, we do have a booth there. We were there all day, so thanks for everyone who dropped in and said hi at the convention, and hopefully we'll see more of our friends tomorrow as well. So, since it looks like we're just about getting over here and getting settled in, a little bit of a safety briefing for everyone who is here. Uh, if you need the restroom, that is the porta potty, it is in the back to my left, your right behind you. It is illuminated by red for ease of finding in the dark. In addition, we have the little museum and gift shop area. I'll be manning that after the talk because despite my repeated ask to be allowed to exist in two places at once, they will not allow me to break the laws of physics as of yet. They said, no, Kim, you are not allowed to illegally break the laws of physics, which is very disappointing. So, it looks like we also have a number of our observers have scopes out on the lawn and or possibly, I don't have my distance glasses on except for my sunglasses, and
We will have 3 observatories open.
perfect. Yeah, I can't see anything beyond a certain distance, especially not with sunglasses in the dark, but we'll have observatories open for viewing after the talk. With volunteers manning those, so feel free to ask them all your fun questions. When we go to leave, we are using our headlights because we don't like being the splat of Frogger in the video game. We much prefer to be healthy and safe. That being said, if we're wandering around with flashlights or our phones out for a little extra light, we do ask you keep the light pointed towards the ground because we do not need to unnecessarily blind people with the latest, greatest Amazon find of unfathomable number of lumens. So, you're not here to listen to me blather on for forever.
You're here to hear me blather on forever?
Well, at least for the next 45 minutes.
For 45 minutes.
So, Paul Fisher here is going to be giving the talk about black holes. Paul has a Bachelor in Engineering and Chemical Engineering from Stevens Institute of Technology and has worked in the environmental and chemical industries. Though he's always interested in celestial objects, Paul's official start in amateur astronomy was one night several years ago, lying in awkward positions on his roof. He's much braver than I. I find roofs to be far too high off the ground. Uh, in the freezing cold, holding a pair of binoculars where he saw a brief, clear glimpse of the Galilean moons of Jupiter. Since then, he was hooked and managed to read through a whole list of books that puts my to be read list to shame. And af- now he is an active member of Northwest Jersey Amateur Astronomers and volunteers here at United Astronomy Clubs of New Jersey, and still yet manages to find time to find himself outside at night, awkward positions, freezing in the cold, seeing neat stuff. Blah, blah, blah. I swear I can talk tonight. Seeing neat stuff in the night sky. And with that, here's Paul.
Hi, everyone. How are you doing today? Like I said, thank you for coming out in this cooler than I don't know whether it's cooler than normal, but it's certainly a cooler temperature tonight. And braving the cold to come out and join us here. Also, anyone online who's listening, thank you. And tonight I have a presentation on the Beatles, right? I've got a hole in my pocket. Who remembers the Yellow Submarine, the cartoon from way back when? Okay.
What's really amusing is we have a young one in the
A
front
young one who
raising their hand.
might not even know who, well, you might like cartoons. And if you have seen the Yellow Submarine, you're awesome already. So, excellent. So this is the remember Blue Meanies were the bad guys in the Yellow Submarine, and here's the eponymous Yellow Submarine. But and that was I named this presentation after a line Ringo said, found a hole, used put it in his pocket, took it out. He said he had a hole in his pocket, and then took it out and saved the band from the Blue Meanies. So I named it after that. But what's this talk really about? Black holes. Black holes are a very interesting thing in astronomy, aren't they? I'm going to demystify them a little bit. And that's me at the bottom there, as Kim said, a member of NWJAA, and I volunteer up here. So who's got the tea on black holes? You know, I'm reporting, but I don't really have the tea, right? I'm an amateur astronomer. I'm not a professional astronomer. This report is loosely based on a video series. The source information is from Dr. Alex Filipenko, Black Holes Explained. I got my hands on the course through the Great Courses. So for any mistakes, blame me. For anything that you find interesting and useful as far as information goes, certainly please credit Dr. Filipenko. The whole thing. So what is this presentation going to involve? First, we're going to kind of talk about what exactly is a black hole, or not exactly, but a little more clarification. Some things about gravity, because gravity is a very important part of a black hole system. Black hole sizes and types, how are they formed? Some facts about black holes. A question that we get asked, are black holes real? And are pictures of black holes real? I mean, how do you take a picture of something that doesn't let go of light? Sounds problematic. Not really, if you define things the way they're supposed to be defined. And what happens if the thing that at one point someone said, "Gentlemen, don't talk about what happens if one falls into a black hole." So what happens if something goes into a black hole? What's happening there? What does LIGO have to do with black holes? Remember, that's the interferometers. We have two of them that have been detecting gravity waves. What will the LHC do bad things when it creates micro black holes? Does it? Does those black hole if those black holes are created, what would they do? We'll talk a little bit about the concepts of Hawking radiation, hair, and S. And anyone who has a technical background recognizes S as what? Entropy, yes. S is entropy. And then extremals, white holes, and other dimensions. And let's see if I can move away from the speaker and get a little bit less interference. So we will touch on those things. They're a little bit more technical. We'll just touch on them so you're familiar with them and not really go into tremendous detail on those things. So we were going to start with, what is a black hole? A black hole is a region of space where nothing, not even light, can escape. Nothing can escape. Anything that goes into that region, its future is guaranteed to wind up in the black hole. There is no technical solution to that. We don't just have to figure it out better how to get away from black holes. There's nothing to figure out. You're guaranteed to go in. Carl Schwarzschild formalized the concept in 1916. He calculated the radius at which light could no longer escape at r equals 2g m over c squared. G is Newton's universal gravitational constant. Black holes are a gravity thing. The above equation can be derived as escape velocity using Newton's physics. In fact, if you just take the c and you put a v there for velocity, that is the escape velocity. You can derive that equation using Newtonian physics, just putting the speed of light in for v. However, there are some problems with doing that, and we'll discuss that in a little bit. Or from general relativity, which is correct? Well, I just gave the answer to you. You have to use general relativity to come up with this equation to do it the right way. Escape velocity doesn't, in a Newtonian sense, does not cut the mustard. First of all, let's talk about some of the pieces of a black hole. Here is the singularity. That's what most people think the black hole is. But the black hole really isn't just the singularity. And now you're getting a view of why you can take pictures of it. It is true you cannot take pictures of the singularity, but you can take pictures of the rest of this stuff. And the black hole, if you consider it a system of things rather than just the singularity, then you kind of understand why the black hole is something that astronomers study, can understand, and get information about, because they're studying this whole thing, not just the singularity, which is very hard to study because you can't get light out of it. There's the event horizon, which is any part past that Schwarzschild. I'm sorry, let me make sure I get his name right. Schwarzschild radius. Anything inside there is not coming back out again, including light. The photon sphere is where light, the gravity is so strong, it's above the event horizon, but just above it, where the gravity is still so strong that light actually orbits the black hole. Relativistic jets, which come out of its magnetic poles. The innermost stable orbit, which is whatever mass you happen to be talking about, is there's a certain point at which if you have any mass above it, you're going to be able to escape. Below it, you're not going to be able to. And then the accretion disk is just all this stuff that happened to be in the vicinity of the black hole that got caught by its gravity and is now orbiting the black hole. But it's a lot of that stuff, since the gravity is so extreme is accelerated so fast that it gets very hot, very energetic, and starts giving off its own light. It's so hot it gives off its own light. Just like anything that you heat up to whatever temperature it takes, will start to glow. The other thing you want to understand too, or that is important to understand how astronomers have found these things and stuff, is that frequently stellar mass black holes will have a companion. If you might not know, but a lot of stars, our star is the sun, is kind of unique. Not unique, but in a smaller category of stars that don't have stellar companions. So we are not a binary system, we are a single star, and it's actually very common for stars to form a binary or even multiple star systems in the same solar system. So black hole companions are, say, another important feature to understanding black holes. The black hole is kind of both in the same worlds as being mundane and also exotic. Black holes, unless you approach them too closely, act as any object of the same mass. So if you were to take our sun, or calculate the mass of our sun first, and then remove it, and then put a black hole in the same place that the sun was, that is the same mass of the sun, what would happen to Earth? Exactly, nothing. It's the same mass. The Earth would continue in its orbit. The Earth would get cold because it's not receiving the energy from the sun. However, we wouldn't immediately feel any effects from that replacement. So at a distance, the black hole acts as any other object of the same mass. It's only as you approach the black hole that the gradient, the change in gravity becomes so extreme because it's a singularity, it's so small, the gravity lines really start to crunch. And so do the things that approach the black hole. But we'll talk about that more. If the sun were, there it is, I said that already. We don't know what the material inside a singularity is made of. It's called a singularity because our physics and math currently do not describe it. Although treated mathematically as a point source, some experts do not believe it is actually infinitely small. If you remember your geometry, a point has no dimensions. A theoretical point in geometry has no dimensions to it. That's what a singularity is treated as mathematically. However, some experts do not believe it's actually infinitely small, so maybe they have some very advanced physics and mathematics to describe a little bit better what's happening there mathematically. However, for all intents and purposes, it's a point source. We are prevented from directly observing the singularity. Again, light goes in, and light means radio waves, gamma rays, all those things. In fact, anything, because light is pure energy. Energy is the most energetic thing. Energy is a massless particle is the thing with the highest velocity. It is the speed of light, and that is the only thing that can attempt to that's the fastest speed it can go. That's the upper speed limit, and so therefore you cannot anything that wants to leave cannot travel any faster than that. And so if light's going in, so is everything else. Gravity concerns. So we talked about escape velocity as derived by Newtonian physics versus general relativity. So the Schwarzschild radius. And how is the correct way? Well, we're going to talk about Newtonian physics or general relativity, and Newton and Einstein. We're going to imagine a little bit of a fight between them. So here is escape velocity. This is the calculation, and if you put the v squared on the other side, you multiply both sides by r, you get r on the other side, and if you uh, divide both sides by v squared, you get the v squared underneath. You get the same equation, right? You just put c in for v, you put the speed of light in for the velocity, and you get the same equation. So what's wrong with that? Let's discuss the previous slide there. Light has zero mass. So what attraction should that wind up with? Zero, right? How does that work? You cannot go faster than the speed of light. Does this equation here, if you put in large enough values, you can have an infinite v squared value, right? You just keep increasing the m values. Does this equation prevent you from doing that? It doesn't. So it's not describing the reality. So you can't go faster than the speed of light is another problem. So what ends up happening is that the derivation of that equation, the Schwarzschild radius, is done through general relativity, and it's done with very sophisticated mathematics and physics. It just ends up boiling down to a very similar equation. And with that very sophisticated mathematics, which I'm not, like I said, I'm a lowly engineer. I'm not a physicist. I don't know or understand those equations, but they describe the physical sense of what's going on here. So let's describe that physical sense and forget about the mathematics. What Einstein has proposed is that it has nothing to do with some sort of mysterious, or it has nothing to do with, as Newtonian proposed, a mysterious attraction force between two objects, and has a lot more to do with the curvature of space that mass makes in space-time. So this is a great picture of what he's describing. This is a massive object. Excuse me. Let's call it a black hole. And it is bending space around it. And as you can see here, as something approaches the object, it has a tendency to fall in that bent space around space-time. And that is a better description of gravity than just some mysterious attraction force. So think bent space-time. And so here is some things where maybe we can talk about which ski trail. If you would describe our sun as being like a bunny slope, and a white dwarf, which is more compact, say our sun, but a lot smaller, to have a bigger bend around it, right? A bigger depression of space-time, a bigger deformation. And then a white dwarf would be, say, an intermediate slope. A neutron star would end up being, say, a black ski slope, and then a triple X here would be your black hole. If you notice here has an endpoint, these three, and then a black hole, you just have you are effectively, say, being taken out of the universe. if you were to go on that ski slope. So it has to do with the amount of distortion. Because it's so small, these lines get distorted much further as you get closer to the object. So Einstein really has a flawless victory. Schwarzschild did base his calculations on Einstein's theory of general relativity. It just ended up with a very similar looking equation. All possible paths, all possible futures lead into the black hole. Even massless light at the universal speed limit of c cannot escape. Black hole sizes and types. So you might have heard of some of these. We have stellar mass or stellar black holes, the end of life of a large star. A supermassive black hole, which is in the center of most galaxies. The weight of a stellar mass black hole typically can be several to hundreds of the mass of our sun. Supermassive black holes can be hundreds of thousands to billions of the mass of our sun. An intermediate black hole, 1,000 to 100,000, so that in between space. And where can we find them? Stellar black holes everywhere, supermassive black holes in the center of most galaxies, and intermediate black holes. There are candidates in places like the center of globular clusters. They are slowly being identified by astronomers as we speak. Primordial black holes, micro to intermediate. These are black holes that did not form, not in the center of galaxies, nor from a collapsing star, but were actually formed by material that was around during the Big Bang, when the Big Bang happened. They were theoretical, or are still theoretical. We're going to say it's none found, and this was their origin just after the Big Bang. However, that's a very meaningful asterisk there, and we will go into that in a little bit. Micro black holes, atomic size to asteroid size, none found, possibly being formed from high energy particle reactions, and there's no asterisk. There's just, we haven't found any. And again, the green here is that the evidence exists. We have evidence. And the yellow is the evidence does not exist. However, again, I will point to that asterisk at the end of primordial. All right, here's the slide on primordial black holes. In 2023, the KM3-NET Observatory in the Mediterranean detected a 220 PeV neutrino. Yeah. Okay. What does that mean? Neutrino is a subatomic particle, and what's weird about this is that it's an unusually high energy cosmic particle. It's 100,000 times more powerful than what the LHC, the Large Hadron Collider, can produce. Some theoretical physicists, the article I read was about the University of Massachusetts, Amherst, but others I think have proposed it earlier. I've been hearing this news for about a year now. And when scientists propose things, they don't just have a weird dream and then show up the next day and start working on it, right? They've done all the calculations, all the math, make sure that all checks out, all that type of stuff, right? There's a long, involved process, and then they release all that information so people can say, yeah, you know, that's legit. It might be something like that. They allow people to poke holes in it. That the source of the neutrino, they propose that the source of a neutrino was an evaporating primordial black hole. The calculations of the energy that this neutrino had were consistent with the prediction of particles coming from a black hole that evaporated. That's very important. And we will go into black holes evaporating in a little bit, but yes, black holes can evaporate. Other observations at other observatories did not detect the particle, but a dark charge theory has been suggested to explain the discrepancy. The science is still developing on this, right? Obviously, one place detecting it, one place not detecting it. There's some room for interpretation there, but it also may have some important implications for dark matter. Specifically, if you're familiar with the argument of what dark matter could be. Machos versus wimps, it supports the machos theory. But that's why the asterisk is there, and it's still theoretical. The science isn't settled on that yet, right? There has to be a little bit of agreement in the science community for us to say that's what it is. And so that agreement doesn't exist yet. This is new science happening right now. So kind of exciting, that asterisk there. How are black holes formed? Well, this is stellars by a stellar remnant. A star collapses into a black hole. Supermassive. They accrete mass and energy. Intermediate accrete mass and energy. So somehow the black hole formed, and then it just started eating a lot of things. Primordial and micro, the mechanism for the primordial primordial black hole is gravity and phase fluctuations during the Big Bang. And then the micro, how does it form? High energy particle reactions, but they evaporate very quickly. And again, the concept of black hole evaporation is right there. All right, so how does an actual star or stellar mass black hole, a star, uh, form a black hole? Well, you've heard of white dwarfs, you've heard of neutron stars. With white dwarfs, electron degeneracy. So this is a concept in particle physics. Electron degeneracy holds up white dwarfs. It's the Pauli exclusion principles. Particles have to organize themselves based on the properties of the particles. They can't exist in the same space and have the same charge and other types of other properties, and so therefore the electrons will in the star will start forming a matrix, and that holds up the incredible gravity pulling a star into itself. So the star at the end of its life of a certain size will stop at as electron degeneracy holds it up, and that's where it spends the rest of its days. If electron degeneracy isn't sufficient, then the star continues to collapse, and then neutron degeneracy holds up. Neutron degeneracy, things squeeze a little bit in more because neutron degeneracy gets an assist from the strong force. So it's a little bit extra. The mass is bigger in the case of a neutron star. It gets pulled in past of the electron degeneracy's ability to hold it up, but then then neutron degeneracy kicks in, and neutron degeneracy, like I said, the strong force is giving it an assist. Beyond those opposing forces, I've got nothing, and then neither does the rest of the universe. That's when the black hole comes in. So the star was so massive that the gravity pulls it in and just keeps pulling past those two degeneracy pressures, and it goes into a black hole. That's a stellar mass black hole. That's how it forms. Here's a supernova nova remnant, W49b, with a black hole candidate in the middle of it. And this is how the supermassive and intermediate black holes get to be where they were. They just accrete. And you see these actors portraying a black hole accreting. That's all it's doing. It's eating stuff. Let's talk about some facts here. What are real evidence of black holes that exist? First of all, something's there. Something is affecting the orbits. Some gravitational interaction is happening, but we can't see it. That's our first clue that there might be a black hole there. That's not sufficient. That just means we didn't detect it, right? So that's not sufficient evidence, but it's our first clue. Then there's maybe an X-ray source from an accretion disk that's coming from a companion. Maybe there's a star wobble happening. Maybe there's missing afterglow from a collapsed star. So these are further evidence. So now we have something that we can't detect and further evidence. Also, gamma ray bursts come from black holes, quasars and other active galaxies for supermassive black holes, spectra broadening when you're looking in the center of galaxies, gravitational waves. We've detected black hole mergers at this point, right? And then Einstein rings or gravitational lensing. We can't see the object, yet somehow an object behind it has been lensed. If anyone has seen the Einstein rings, or there are natural telescopes in the sky. Galaxy clusters, galaxies, black holes can actually focus the light. And we can see much further back in the further away in the universe than previous, or we otherwise could. So here's a star wobble. Imagine this guy here is a black hole. So we can't really see it, but for demonstration purposes, it's there. And then we have the star, companion star. If the star is doing this, but we can't see anything, that's evidence of a black hole. Because what's causing it to do that and we can't see it? Possibly a black hole, right? And so the star will do this according to our readings. And this is the spectra. This is redshift and blue shift, back and forth, back and forth. The hydrogen, say, coming from this star will wobble back and forth. The light spectra will wobble back and forth like that. Kind of cool that we can detect that, right? Have to know a lot of physics, right? You have to know about spectra and all that type of stuff. So all that science stuff, sort of adds on to each other. Gamma ray bursts. This is just a demonstration of a gamma ray burst from like a supermassive black hole there with a pretty large, or any black hole really, with an accretion disk. So that accretion disk has a pole as it circulates around, and that gamma ray burst, when something falls into the black hole, is another point of evidence. Quasars. So we've noticed that the further away we look from our planet, quasars, or very active galaxy centers. So there's something called the active galaxy centers, which are around here, and then quasars, which are extremely active. We notice this pattern, that the further away you get, there isn't any, and the closer you get, there isn't any, and then it follows this curve. What is this? Okay, we cheated. It's called the cosmic time, billions and years, but this is in light years. But light years refers also means how many years ago it was, billions of years ago. And so what's happening here, they figured out eventually, or have theorized, that this is when a supermassive black hole in a galaxy had lots of stuff to eat. All the stuff in the galaxy was falling, and then it just started eating everything in its vicinity, and then it just sort of stopped because it ate everything in its vicinity. And so that's why these quasars and active galaxies are evidence of supermassive black holes, because that fits the physics of what's happening. There's the spectral broadening, okay? Similar to how that star wobble was giving us a blue and red shift, the same thing's happening here on this accretion disk around this supermassive black hole. Here's the supermassive black hole. These are redshift, so the observer's over here somewhere. These are redshifts, so this material is rotating around this way and is moving away from the observer. The material on this side is moving towards the observer. Moving away gives you a red shift. Moving towards you gives you a blue shift. And what's that effect called? The Doppler effect. Someone whispered it over there. The Doppler effect. So you've heard of that. You've heard it related to sound. It also happens with light. It happens with any wave. Here's real data. All right, so this is the nice theoretical data where you see the red shift and the blue shift, the different peaks, nicely laid out. And real data is a little bit messier, but you can still see them. Takes a scientist to figure out, what's legit data, what's not, what to include, what not, all that type of stuff. But you end up with a real result. So are the pictures of black holes real? Well, we've learned that the black hole is a system. So we are not seeing the singularity, correct? We can't see it. We're forbidden from seeing it. Physics doesn't allow it. But what are we seeing here? The accretion disk. Exactly. So the pictures of the black hole system, the pictures of the singularity don't exist. You can't. The pictures of the system do exist. They're real. Now, someone might be skeptical and say, man, we're really lucky here. We have these two pictures. This is Messier of 87. This is Sagittarius A. So this is actually three pictures. Two of them are the same black hole. One of them is another black hole. Man, we're really lucky that we got them face on. You know what I mean by face on? That means that, like if you see the rings of Saturn, face on would be you see them in a circle. If you see them edge on, you would just see it as a line. So it's like looking at a plate from its side or from the top. And in space, things are just randomly situated, right? They're randomly positioned. They don't have to face us. They don't have to be facing on the edge. They are just facing in random directions. So what's the likelihood of both of these objects facing us? But you forgot about the photosphere. So when black holes, you're actually seeing light from the entire system all being directed at you, because all light is going around the black hole, orbiting it, and then coming off in random directions. Any of the light that escapes, that hasn't quite achieved the Schwarzschild radius. So that's why they look face on, because that is the light that's actually orbiting the black hole and then coming out happens to be coming out in your direction. It doesn't have to, it's coming out in every direction, but we're only seeing the light that comes out, obviously, in our direction. Okay, video. This is the Sagittarius A picture visualization. Okay, what is Sagittarius A star? That's the supermassive black hole in the Milky Way. What were those things that you saw at the end there orbiting? Stars. So that object, you saw the curvature of that object. That object is so heavy, it's taking stars and flinging them around like it's nothing. We have actual pictures of that happening. Those pictures were taken over the course of years to capture that. We have actual video of a black hole. We can't see it, but what else is causing that? Oh, sorry about that. Let's stop that. And hopefully we can move on to the next slide here manually. All right. What happens, if you get a little too close? In the case of stellar black holes, spaghettification due to extreme tidal forces. Again, remember, it's not the overall gravity that's the problem. It's how tight those gravitational lines get and how spread out. Remember, it's gravity's appears to be coming out of that point source radially. So as you get close, as you're far away, everything's leading straight onto the black hole. But as you get closer and closer and closer, the further the gravitational lines are diverging, and they eventually diverge to a point where just your small body experiences extreme differences in the gravity. So your head and your toes will experience a very big difference in gravity, and that big difference can pull apart normal matter, which I think we're all here, you would agree, we're all made of normal matter. In the case of supermassive black holes, it's a different effect. You pancake. That's because they are so big that those gravitational effects happen further out away from the black hole. Maybe they come into contact with highly energetic accreting matter. Now remember, this is matter sped up to the point where it glows so much that we can see it from, hundreds of millions of light. Let's see. In the case of Sagittarius A, like tens of millions of light years to hundreds of millions or billions of light years away. Time dilation will also happen. Matter from objects in black hole gravity fields will appear. Anyone who's seen what's that famous movie? Interstellar. Thank you very much. Time dilation. Matter from objects in the vicinity of a black hole gravity will appear to slow down and eventually freeze in time, and then get dimmer, dimmer, and dimmer, and dimmer until. All right, so let's take a video break and see what happens if we have a magic camera that can still transmit out of the black hole. So there's the camera going into the black hole. That's all the light from the universe you can now see in front of you. Everything behind you, everything on the other side of the black hole, everywhere. Light is so distorted that those effects happen. Kind of cool. Theoretically. For these visualizations, you can go to the NASA Plus website and uh, other websites to download those videos. They're kind of a cool reference. What does LIGO have to do with black holes? Remember, LIGO stands for Laser Interferometer for Gravitational Wave Observing. California Institute Technology and MIT are partners there. Detects gravitational waves from distant interactions of massive objects. There are 2 locations, one in Washington, one in Louisiana. Why do we have 2 of them? So if one detects one and the other one doesn't, we don't consider it an event, or humanity doesn't consider it an event. It is only an event if those 2 separate interferometers detect the signal. The first detection was in August 17th, 2017, and so far it has detected 83 black hole mergers, 2 neutron star mergers, 3 neutron star and black hole mergers, and 2 mystery mergers that they're working on theory for. And that is a year-old data, so it might be even more now. So quite successful doing that detection. Here is there's at a right angle, and you can see the size of this thing, right, from aerial photography. It's huge, and it detects the change in the length of an object. Gravitational waves will make things smaller and bigger. It can detect the length change in the laser that is posted from here to here, about 1 kilometer, I think it is. No, 4 kilometers. 4 kilometers. It can detect the change in difference of the size of a proton. Very accurate instrument. So kind of cool, detecting black hole mergers and other massive objects. Here's what they're detecting, right? This is 2 objects getting close to each other. They start to disturb space-time, like Einstein theorized it would. Einstein theorized these gravity waves, and we detect them now. The other question here, so that's what LIGO has to do with black holes. What does the LHC, the Large Hadron Collider, have to do with black holes? Will it produce micro black holes that end up doing bad things to the Earth? The Large Hadron Collider is based. CERN is the organization. It's based in. I'm going to butcher this. Meyrin, Switzerland, near Geneva, and on France's border, or on Switzerland's border with France. And it's the world's largest and most powerful particle accelerator, conducting multiple particle physics experiments. It's starting to ramp down a bit now on how much they're doing there. It directs 2 beams of protons that are accelerated to 99.9% the speed of light to collide with each other. Collisions with a normal energy of 13 TeV. July 4th, 2012, it announced the discovery of the Higgs-like particle. You might have heard of the discovery of the Higgs boson. So this is an interesting, you thought the other instrument was big? So this is a particle accelerator that's shown on a map. That's how big this guy is, except this isn't the guy. This one is the guy. This is another particle accelerator that pre-speeds up the particles and then feeds them into the LHC. So it's even bigger than this map. So that's a big piece of equipment. Here's what it looks like on the inside. It's just this tunnel going for many, many, many miles. Okay, and so let's talk about who here has any background in, say, industrial safety and has participated in a HAZOP or any sort of safety review where they work. No one. Okay. Well, I've done a few, but I just
Are you OSHA approved?
well, it's not really OSHA. It's sort of like due diligence when you start up a new system. You don't want to hurt anyone, right? So you do a safety review of it. So they didn't want to hurt anyone, meaning they didn't want to destroy the earth. So imagine that being your safety review. Are we going to destroy the earth by starting this thing up? According to well-established properties of gravity described by Einstein's relativity, it is impossible for microscopic black holes to be produced at the LHC. That's a direct quote from CERN, and in a little blurb they had about the safety, or a little bit of information packet they had about the safety of the LHC. Furthermore, CERN and Professor Philip Penko also point out micro black holes would evaporate into in tiny fractions of a second after they form. So that evaporation thing is happening again. We'll get into it in a second. So micro black holes are so small, they evaporate so quickly that they couldn't possibly pose any harm. And then even with a factor of safety of many magnitudes, a micro black hole that is somehow stable, somehow doesn't evaporate. So they even went further and say, hey, what happens if we got that evaporation thing just wrong? Right? They said it would accrete matter at such a small rate, this again being a micro black hole, that we wouldn't have to be concerned for the safety of the planet, for the expected lifetime of the planet. The planet has what, another I think it is a total life of like 7 billion years, and we're 4.5, so we got like 3.5 billion years or 3 billion years left. So the micro black hole couldn't eat enough stuff to be dangerous in another 3 billion years. So there's no real safety concern for the LHC as far as black holes are concerned. Let's talk about that evaporation thing, and that's where Stephen Hawking, you might have heard of him, comes in. Stephen Hawking, just so you know, particle physics again, particles are constantly rearranging themselves and resizing themselves into different particles, and they're sort of an agglomeration of stuff that end up averaging out to whatever we consider that particle to be. They're constantly changing into different particles. They're constantly being created. It's called vacuum pressure in a vacuum, and then disappearing immediately because you can't create energy out of nothing, excuse me. So they form in a pair, and then they destroy each other. The particle and antiparticle spontaneously form, and then the particle and antiparticle end up destroying each other, and the energy ends up balancing out. But what happens, we talked about the Schwarzschild radius, what happens if one of those particles that was spontaneously created from a vacuum ended up falling into the black hole, and the other one was on the other side? Then one of them would escape. One would go into the black hole and one would escape, and so therefore black holes radiate. This Hawking radiation ends up evaporating the black hole as this happens often enough. Smaller ones happen faster. There's just less mass to get rid of in this manner. All right. So what does hair have to do with it? Let's talk about. Let's go into it real quick. But this is where the hologram theory comes about from black holes. There is that information in physics is supposed to not be destroyed. Yet in the black holes, it seems like whatever went into the black hole just becomes part of the black hole, and all that information that made that thing what it was disappeared in the universe. What happened? Well, that hologram theory related to the Hawking radiation, that you could read this hologram layer on the surface of the Schwarzschild radius, and you could reconstruct, theoretically. It would take a computer many times the size of a good portion of our galaxy, or something huge. It would take lots of computer power that we don't have, and reconstruct that the data that created that object. And just so and we talk about entropy, if you take something and you jumble it up, or you take a system of things and you jumble it up, and you can no longer tell the difference between the objects, that is called entropy. You have made those things completely homogeneous, and can't tell the difference between one thing and another. If you take things together, jumble them up slowly, and they're still organized in the way you were, you did not increase entropy. You maintained order. It's called a reversible process, and you have zero entropy. And black holes are the ultimate expression of entropy. They just take everything and make it into black hole. Extremals, white holes, and other dimensions. Extremals are just, it's the terminology physicists use for a black hole that doesn't have any spin, or has very high spin, or no charge, or high charge. Physicists use these extreme mathematical situations to help bind problems. It says, well, it certainly would be no more energetic than a black hole with high spin. And so they bind the problem. They say it's no greater than this situation, no greater than that situation. So it's a tool used by theoretical physicists to help understand any black hole problems. White holes, the theoretical, or proposed anyway, the other end of a black hole. Are they possible? Could they be stable? Could something travel through them? Dr. Filipenko goes into this a little bit. There's some interesting diagrams associated with it. I don't think I understood it perfectly well. I think you have to have a little bit of more of an introduction to theoretical physics to truly understand it. Though he did, he did, I got a little glimmer of understanding from it, but I suggest you watch it yourself, because I might say something completely wacko and throw you off the trail on that. So if you have interested in white holes, go to the source. And what are the implications if micro black holes are detected? Would their fluctuations of gravity imply other dimensions? So in a spooky sense, excuse me, in another sense, again with those diagrams, Dr. Filipenko talked about the existence of micro black holes could mean that there are other dimensions, not just x, y, z, and t, not just the x, y, and z coordinates plus time, but other dimensions too. It could be a proof of concept that other dimensions exist that we just can't detect. So interesting there. I highly recommend the series, Black Holes Explained. Dr. Filipenko did a great job explaining it, and I found the black holes very interesting. Hopefully, you do too if you take a look. And thank you, everybody.
All right. Thank you, Paul, for another great presentation. So, we are going to be doing a question and answer session. Wow, I sound like my voice is starting to go. Uh, but before we get too far into that, since I did see a couple people sneaking in after I had done the safety briefing, and the safety briefing is unescapable, uh, if anyone here needs to use the bathroom, it is the porta potty in back. To my left, your right, it is illuminated by red for ease of finding in the dark. We also have a little museum and gift shop area that I will be manning after Q&A, because I can't be in two places at once. We do have a number of our volunteers have scopes set out on the lawn, and we'll have a couple of observatories open for viewing of the night sky. I do encourage everyone to ask questions of our volunteers and go check that out. When we go to leave, we are using our headlights because ain't no one have the expendable income for the medical bills of getting run over. So let's avoid that. That being said, if we need flashlights or whatnot to walk around in the dark, because it is a state park and it is quite dark, do try and keep those pointed towards the ground. We don't need to accidentally blind people for no reason. So, with that, how question and answer session's gonna work is for the people here. You're gonna raise your hand and kind of wave it about like you just don't care, and keep your hand raised. Otherwise, I lose you in the dark. Uh, I have no night vision currently because I've been monitoring online chat. Speaking of online chat, you guys have it easy. You just get to type, and then I'll read it out. So get this party started. The first online question is: so black holes are where things are exceedingly compressed into a massively dense point. Are there any things that are the opposite, where things are so not dense that there is almost nothing?
Well, I mean, you just described space. Uh, but is there like we did mention white holes? Is there the antithesis or the end of a black hole? And some people have proposed that. I don't know. I don't know of any uh, serious candidates or anything like that on where a white hole exists. So in the sense that space is not full of nothing, because we did talk about quantum fluctuations, but it is the least dense of our existence. But as far as white holes go, we just have no evidence that white holes exist.
All right, and questions out here. All right, let me hand you the mic.
So I'm a little confused about how black holes appeared so early, when the universe was just born, as in supermassive black holes, because there is a limit called the Eddington limit to how much they can accrete at a time.
Hmm. What is a premortal black hole? It's a little more detail on its origin. That's your question? So what you do know that the theory of the Big Bang, we were an extremely dense existence. The universe was, and then it expanded. It went through expansion, and then became this extremely not dense. So there was an in-between state where we were, say, at a state where things were extra energetic, but there were interactions. So it was right after the Big Bang when we started forming some matter, that the gravity fluctuated. It wasn't necessarily all homogeneous. There were may be fluctuations there, waves, or some sort of variation going on. And at some point, it was really dense enough that it just bypassed a normal matter state and it fell directly into a black hole. And those primordial black holes could have been theoretically any size. And the reason why we've been looking for that evaporation of happening is that there theoretically could have been some pretty small black holes that it only took 14 billion years for that black hole to evaporate. And so we should be seeing evaporating primordial black holes now had they existed from the Big Bang. You're welcome.
All right. Our next online question is the speed of light really the max speed attainable? Sci-fi often features faster than light travel methods. Are there potential scientific conjecture there, or is it just a flight of fancy?
Yeah, no, it's yeah. Um, as far as our physics goes, we are unable to describe any situation at the moment. I think through certain media, uh, you can travel faster than the speed of light through vacuum. However, those are very specific cases, and it's still at a limit. It's still, it's just a different limit. So if you think about it, there's a good, you might look this up online, but there's a good argument that there has to be a maximum limit. Otherwise, space and time would have no meaning. If there was no limit and you could just travel anywhere, then what's the purpose of distance and what is the purpose of time? Could it exist even? So the fact that there is a limit actually makes logical sense because we do have space and time, and it is meaningful to us. So therefore, I'm as again not a professional scientist, not a professional physicist, but I'm of the opinion that there's no free lunch. We do have this limit, and it's just something that we will not be able to overcome. Now, whether those extra dimensions or extra universes or any of those things ever pan out, that's highly theoretical stuff, and we would actually have to see some experimental evidence to understand it and see whether or not we could ever make use of it. But right now, our physics just does not allow us to exceed that limit. Our understanding of physics, it just exists, and we have to deal with it.
All right. Any more questions? We don't even have the crickets because it's a bit chilly out right now. So our next online question is uh so they're confused. Space is a vacuum, a black hole is dense. Does the superheated particles on the perimeter of the holes create containment? And before you get into the answer, one of our online viewers tried to help answer this, and we're going to see if they're kind of close to a basic high level understanding answer. They believe, the other online viewer said, they believe the gravitational pull of the central point is more acting like a leash than the stuff on the outside acting like a fence.
Okay, I mean, it's just an orbit around a massive object, just as the Earth. Uh, uh, you know, it's you're constantly falling. You're always falling. You're just moving fast enough that the Earth is a sphere. You are just moving fast enough that the direction of the fall has shifted to move you further along the radius of a circle. So it's just a happenstance that you're falling, but you've moved. And so you're again at the same distance because you're moving around a circle. So you're constantly falling to the Earth in the orbit of an Earth. This is the same thing happening. That stuff is orbiting the black hole. And it's just moving fast enough that it's not falling in because it changed position.
Right. Uh, Guys, again, if you have any questions, do raise your hand. I'm gonna, since everyone has their hands like shoved in their pockets, I'm gonna try and get through some of these online questions. This next one was a fun comment I thought you would get a kick out of. Micro black holes. What temporarily opens up in a teenage boy's stomach whenever food is around?
Yeah, I think that black hole actually lasts for a good 5 6 years, right? As a teenager finishes growing. Yeah, that is true. That it does seem like an empty pit that you can never fill. But yeah, yeah, it's a good whimsical analogy.
All right. So our next actual question is, what actually creates the quote unquote winning team of gravity?
The winning team.
Yeah, I don't
I
know.
mean, it might have referred to the Newtonian versus the general relativity, right? So you have to realize that when you're doing things technically, you have to frame them in a mathematical construct that makes sense. You never are describing reality. Reality is as big as the universe. You are never exactly describing reality. We use mathematical and science models to understand and make predictions about what's going on, but you are never truly describing reality. So who wins? Who's really the winning team? Newtonian physics or general relativity? Well, for many things, most things, Newtonian physics works just fine. Use Newtonian physics. But for some things,
Except for non-Newtonian fluids.
well, except for non-Newtonian, applications. For instance, the GPS is a very famous thing that everybody uses that requires both special and general relativity to make it work. So you use what works. Is basically you're using the model you need to understand and make useful predictions in order to build something or understand something.
All right. So, online people, I just want to do a last call for any questions from there because you'll finally hear that when we start this next question.
So, when the black hole evaporates, does all the matter it took in go out with it, or is it just in there?
That's an awesome question, and I don't know the exact. However, I did read a little bit into the article, and as it evaporates and gets smaller and smaller, it starts heating up and spewing out more matter. And it ends up, I believe, in an explosion. Is at least according to the article. So the black hole exploding. I'm not exactly sure what the description of that explosion is. However, that was what I read in the article, and this article happened on the 8th of April this year, so not too long ago, from the University of Massachusetts. Maybe you can find the article and explore that yourself. And I'm not going, and you probably might even have a better possibility of understanding it than I do. Again, this is particle physics. This is astrophysics. It is beyond my expertise, and it's cool stuff. And maybe you can get excited about it. And I don't know how old are you, sir? 12 years old. Well, maybe you can get really excited about it and become a astrophysicist. It's the article I read. I think it was Science Daily, which I looked up to see whether that's a reputable source, and it seems to be a reputable source. And it's a general source for science, not in the specifics. It talks about the abstracts. It doesn't get into the technical details of the papers. However, it was April 8th, and it's the University of Massachusetts. So look those things up and talk and ask about primordial black holes, and it should lead you to the article. Hmm.
All right. Any last minute questions out here? Ooh, we got one.
So this isn't really about black holes, but I have binoculars, but I don't have a telescope. So could I just use that instead for like looking at the stars?
Oh, you know what? Jupiter, if Jupiter's still up, Jupiter's a great object to. Here's a tip: hold it by the end, by the object side, so far away from you, not far away from your eyes, but uh, the opposite end. Hold the binoculars to help stabilize it from the opposite end, and point it at Jupiter, and you'll not only be able to see Jupiter, but you'll see the Galilean moons, and they are cool. You know what I mean by the Galilean moons? The
Well, you
moon,
mentioned it at the beginning. I'm pretty sure.
the
So.
moons that Galileo saw, and then started everyone thinking about the solar system, what its true nature is, and how gravity really works.
Oh yeah, I'm pretty sure I learned about that in like science class or something.
Yeah, but you will be able to see that with your binoculars if Jupiter happens to still be up.
All right. So be a hello. There we go. All right, Paul's gonna be around for a little bit. So feel free to try and stump him with any questions you have. I do want to thank everyone who's not only come here but joined us online. Like I said, do check us out on our website, uacnj.org. It's where you'll find a plethora of information, not only about us as an organization, but also our member clubs and our upcoming talks. And also follow us on our social media. Hit the like and subscribe on the YouTube and Twitch streams. Also, we are fundraising to build the shed that'll house our 25-inch telescope. So you'll find out more information on our website about that as well. With that, I wish everyone a great night, clear skies, which we actually do have tonight, and good seeing.
Thank you, everyone, and have a good evening.